Hi everyone. So in this video I'm going to talk about the TLC of analgesics experiment. And the truth of the matter is not all the compounds we're going to try to separate are analgesics. But I do want to go through some of the basics of TLC, and I also want to give you guys some idea of what exactly we're trying to accomplish in this experiment. So before I do that though, I want to remind you, as I said in my introductory video, that in the lab manual there are this at the end of the experiment, before the part where you write down what you did, there are this introduction and conclusion section. There is an introduction conclusion section, and I'm not going to read these, but they basically tell you things that should be in the introduction and the conclusion. I would strongly recommend that you read through this, especially the introduction, jot down a few ideas, maybe not the whole sentences, but the gist of the sentence in a few words. And then as you watch through this video, try and think about those things and maybe jot down some notes that will help you to write your introduction after. I have a bad feeling that if you try to do it, from a whole half an hour video or whatever this ends up being, it could be a little bit overwhelming. But if you do it kind of as you go, it might be a little bit easier. And if you get some notes, that should help you out. All right, so basically what I want to talk about is TLC, thin layer chromatography. So there's two kind of ideas here. There's the practical, what am I actually doing, and there's the kind of theoretical, or what are the molecules that are on this TLC plate experiencing. So I guess it's probably a little bit easier to talk about the physical setup first. The physical setup is we have this TLC plate. Okay, that's this thing here. And basically it's a piece of plastic paper. It's not made out of paper, but it's a piece of plastic sheeting, okay, that is covered in something called silica gel. Silica gel is essentially clean sand, okay? It's like a white, clean sand. And what you're going to do is you're going to spot your samples on this TLC plate. Needless to say, you're going to do this while your TLC plate's sitting on the bench. It's not going to be sitting inside the eluting chamber when you do that, but you're going to spot your samples on this TLC plate. Then you're going to put it into this, what we call an eluting chamber, which has a small amount of eluting solvent. And the eluting solvents are all going to be relatively non-polar, but they're going to be essentially increasing in polarity, or at least have different polarities. And these eluting solvents are going to pull through this piece of paper. And what you're going to do is, by capillary action, you're going to allow the solvent to draw up through this TLC plate. It's not made out of paper again, it's made out of a plastic sheet with silica gel on top. And basically it's going to draw up by capillary action until it gets to the top, and then you're going to stop it. What else we have in here is a piece of filter paper, just to try to keep the environment damp so that this doesn't evaporate. And we have a watch glass on top, again, to keep it damp. A damp environment, so that it doesn't just, the solvent just evaporate off the plate. It continues to go up through the plate. That being said, these are flammable solvents, so you do want to use caution with that. So this is practically what you're setting up. And now let's talk a little bit about what the molecules are actually experiencing. So if we look here, silica gel is a stationary phase. The silica gel on the TLC plate doesn't move. The mobile phase, one mobile phase that you're going to use, is ethyl acetate. And ethyl acetate looks like this. So if you've had organic chemistry, if you put an H there, that's acetic acid. If you put an ethyl group there, it's ethyl acetate. Instead of acetic acid, it becomes acetate, but it's ethyl acetate. This is a relatively nonpolar solvent. This solvent is actually immiscible with water, meaning it won't mix with water. It's less dense than water, so it does form two layers. So this is relatively non-polar. And then this is also the mobile phase. And why is this the mobile phase? Well, this is the mobile phase because it's the solvent, so it moves up through the TLC plate. Then what we're going to use as the stationary phase is silica gel, which again is basically clean sand. Silica gel, okay, which is polar, and it's the stationary phase. So what's going to happen? Well, I mentioned before that you're going to spot your TLC plate with your analytes of interest, and they're going to experience forces from the mobile phase, right, intermolecular forces, and intermolecular forces from the stationary phase. So if you have, for example, a relatively polar analyte, then what's going to happen? It's going to have relatively strong interactions with the polar silica gel. And what is ultimately going to happen is it's not going to move very far because the silica gel isn't moving. So the silica gel is basically stationary. It is stationary. And when the analyte of interest sticks to the silica gel, it doesn't move very far. So if we look at the TLC plate, a polar solute may only go to here or may only go to here. What about a nonpolar solute? Well, in the case of a nonpolar analyte, a nonpolar analyte may not want to interact with the silica gel very much. Why? Because it is polar. Silica gel is polar, so it's not going to strongly interact with the nonpolar analyte. You may remember the term, and it's similar, like dissolves like, which means that polar and ionic solutes dissolve in polar solvents. Another way of thinking about this is polar and ionic solutes have a strong affinity for polar solvents, and nonpolar solutes dissolve in nonpolar solvents. So nonpolar solutes dissolve in nonpolar solvents. So how does this relate to this? Well, what's happening here is the silica gel is polar. So polar analytes, they're not exactly solutes, but polar analytes stick to the polar silica gel. Nonpolar analytes do not stick to the polar silica gel. What ultimately do we see? We see that polar analytes maybe go this far, and nonpolar analytes maybe go this far. Why? Because these polar ones are more strongly sticking to the silica gel, and these nonpolar ones are not sticking to the silica gel very much. Let's take an example. Okay, let's take an example of a compound like naphthalene. This is naphthalene. And let's take another example of a compound like benzoic acid. So this is naphthalene. And this is benzoic acid. Okay, so these are the two different analytes in this example. Let's look at their relative polarity. Naphthalene only contains carbon and hydrogen. So this is relatively nonpolar. Benzoic acid has an OH group and a carboxylic acid group, and it does have some carbons. So relatively speaking, this one is much more polar than this one, because an O bonded to an H, as you learned in Gen Chem, is very polar. Also, the C double bond O is polar, and the ring has some polarity. This isn't completely nonpolar, but relatively speaking, this one's polar and this one's nonpolar. So let's see what happens if we take a silica gel TLC plate and we put these two compounds on here. So for naphthalene, I'm going to abbreviate it NAPT. And for benzoic acid, I'm just going to abbreviate it BENZ, like that B and Z. What's going to happen? We stick this into our eluting chamber, and we elute our nonpolar solute through this. Which of these two things is going to go further? Well, the naphthalene is going to go maybe this far. Now, I'm not saying it's going to go exactly that far, but the solvent maybe will go this far, and the naphthalene will go relatively close to as far as the solvent. Why? Because it's not sticking to the polar silica gel. It's sticking to the nonpolar, moving, eluting solvent. What about benzoic acid? Well, benzoic acid is more polar than naphthalene. So benzoic acid is going to be more likely to stick to the silica gel, which means that even though the solvent travels the same distance for both compounds, maybe the benzoic acid only travels this far. Now, I'm not saying these are the exact amounts, and it would depend on what the nonpolar solvent is, but you get the idea. Naphthalene travels very far because it has a stronger affinity for the nonpolar mobile phase. Benzoic acid travels less far because it has a greater affinity for the polar stationary phase. And you could say these both the opposite way. This one has a relatively weak affinity for the polar stationary phase, and this one has this weaker affinity for the non-polar mobile phase. So that's essentially how it works. And I dropped my pen here, so sorry about that. All right, now let's look at another example. What if we took on a TLC plate and we eluted a mixture? So a mixture of both of these two compounds. Well, in a mixture of both of these two compounds, what's going to happen? Assuming we use the same nonpolar solvent, the benzoic acid will travel approximately this far, and the naphthalene will travel approximately this far. So what has this allowed us to do? It has allowed us to separate a mixture of two compounds. So we started with a mixture where both compounds were in the single spot, and we were actually able to separate them because the naphthalene traveled further and the benzoic acid didn't travel as far. So a mixture allows us to separate these compounds. Now there's a couple of things that we need to be aware of when we're doing this. The first thing is that both naphthalene, which is found in mothballs, so has a distinct smell, and benzoic acid, whose sodium salt is found in beverages because it's antimicrobial type of compounds, and you find it in like soda or something like that to keep the bacteria from growing. These two compounds are both white. So silica gel is white, and these two compounds is white. So you have white on white. You can't see it. How are you going to visualize it? What we're going to do is we're going to allow the solvent to dry by just simply placing the TLC plate in the hood and leaving it for a few minutes. And then we're going to visualize it with UV light. The UV light will show distinct colors of these spots. So we are going to then visualize these spots, and we'll actually circle them with a pencil when we do that. It's also important to note that when you're doing TLC, you have to always use a pencil. A pencil is made out of carbon, and the carbon will not dissolve in the solvent. So essentially, it'll just stay. If you make a line, it'll stay. If you use ink, ink is made out of molecules that can elute on TLC. So if you use ink on a TLC plate, you're going to make a mess. All right. In fact, on purpose, in another experiment in this course, you will use ink as a way to analyze the ink samples. So a couple of things by way of quick review. First, analytes travel different distances on TLC plates based on their relative polarity. Second, if we have a mixture of compounds and we can separate the two compounds from one another, we can separate out a mixture, which is very important if we're trying to analyze whether something is a pure substance or a mixture. Furthermore, if we elute this with where we separately have naphthalene and benzoic acid, if we elute the mixture, the distance the benzoic acid travels is the same in both cases. And the distance that the naphthalene travels is the same in both cases, which at least gives us some idea of identifying that this mixture contained benzoic acid and naphthalene. Now, is this an absolute definitive test with no further testing required, like, for example, using a GCMS? No, definitely isn't. But it's a relatively good confirmatory test, or at least preliminary test, to say, hey, there's a good chance that this mixture contains both benzoic acid and naphthalene. Now, let's look at how we quantitate this. Let's say that we have a TLC plate like this, and say we have a original spot, and then we elute it, and we get another spot that goes that far, and our solvent goes about that far. We'll call the distance that the spot traveled A. And normally you would measure from the line you make across your TLC plate before you place the spot, which again has to be done in pencil, to the center of the spot, which is kind of hard to show here, but it should be to the center of the spot. And we'll call the distance that the solvent traveled from here to here B. To quantitate this, we calculate something called the RF, or the retention factor, and it equals A divided by B. It's essentially a proportion. Okay, so this one, it looks like it's 60%, so the RF would be around 0.6. You can measure this, usually in centimeters, using a ruler. So you measure from the line that you make where you put your spots to the center of your spot, that gives you A. From the line to however far the solvent traveled, gives you B. Note that to visualize the spots, you need to dry the plate and then put the UV light over it. So it's very important that you mark your solvent front as soon as you remove your TLC plate from the eluting chamber. Otherwise, you may not know where the solvent went to. So in this case, you get RF equals A divided by B, and it's always going to be between 0 and 1. If the spot doesn't move at all, it's 0. If the spot moves as far as the solvent front, it is 1. Note that the spot can't possibly move farther than the solvent because the solvent is what's drawing it through the TLC plate. So you're going to calculate these RFs for A divided by B. All right, so the next thing that I would like to talk about is what are we actually using in this case? So in this case, we have two different things going on. The first thing we have going on is the compounds. And the compounds we have are ibuprofen, acetaminophen, diphenhydramine hydrochloride, caffeine, and aspirin. Ibuprofen, acetaminophen, and aspirin are common, pain relievers that you can buy over the counter. Caffeine, I think everybody has heard of, and caffeine is a compound you find in coffee or Red Bull or whatever. Diphenhydramine hydrochloride is an antihistamine found in Benadryl. So these are just different over-the-counter drugs. In this course, of course, we're not going to be using things like LSD, which might be analyzed by TLC in a forensics lab. So we're going to use, analogs, if you will, but the concepts are exactly the same. And you're going to spot these compounds, essentially 1, 2, 3, 4, and a mixture, and you might have to spot the fifth as well. I'm not sure exactly how you're going to get the 4 or the 5 compounds, so you might need to spot the fifth compound as well. You're going to spot a mixture, and then you're going to spot an unknown. And then you're going to elute these compounds. Now, in the case of naphthalene and benzoic acid, it was obvious that benzoic acid is more polar than naphthalene. In the case of ibuprofen versus acetaminophen, it's not quite as obvious. In this case, you have a carboxylic acid group in ibuprofen. You have an amide and an OH or a phenol type group in acetaminophen. Or caffeine, where you have these amine groups and amide groups. In the case of diphenhydramine, it's actually an ionic compound because you've protonated this nitrogen. So these compounds are not as obvious which one is more polar and which one is less polar. But the TLC data will probably give you some idea of what's going on. So what you're going to do is you're going to try 4 different solvents. So you're going to use these compounds and you're going to elute them with 4 different solvents. In the first case, you're going to use ethyl acetate. In the second, you're going to use ethanol. In the third, you're going to use 25-to-1 ethyl acetate and ethanol. And in the fourth, you're going to use 25-to-1 ethyl acetate and glacial acetic acid. Now, it's very, very important that you set this up so that you can elute a bunch of TLC plates all at the same time. If you try to elute one TLC plate at a time, and you have to do at least 2 TLC plates to do the compounds, as well as 4 different solvent mixtures, that's going to be like 8 elutions at least, and that's going to take a very, very long time. So you're going to want to set it up so you can run 3 or 4 or I don't know if you're going to be able to do 8 elutions at the same time, but 4 would seem like a good number, and then do it twice, okay? Because it is going to take some time for these things to elute. Now, if you've had organic chemistry lab, we usually give you the eluting solvent that will work and separate the compounds. But in real life, it doesn't work that way. The eluting solvent that works is empirical, meaning it's research-based. You literally take the compounds, you put them on the TLC plates, and you elute them. So therefore, you basically see what happens. And that's what you're going to do here. Now let's take a look at the different solvents, and let's rank them in terms of polarity. Ethyl acetate, as we already talked about, is a relatively nonpolar solute. Okay, so this relatively nonpolar solute is probably your least polar, or excuse me, relatively nonpolar solvent is probably your least polar mobile phase. Ethanol, with its OH, which is capable of hydrogen bonding, is more polar than the ethyl acetate, which to some extent is also capable of hydrogen bonding, but not with the hydrogen, only with the oxygen. So this is less polar, this is more polar, and acetic acid is probably even more polar than ethanol. Acetic acid also has the potential to dimerize with other carboxylic acids, which could change their polarity. So what you're going to do is you're going to elute these different compounds with these different solvents. And you're going to make an interpretation of what you think is the relative polarity of these compounds based on these solvents. Furthermore, based on your evidence that you've gathered by eluting these compounds with these 4 different mobile phases, you're going to either one, say, hey, one of these things worked great. It separated all 4 or 5 compounds, no issues, and we should use that solvent if we have a mixture of these compounds and we want to separate them. Alternatively, none of them are going to separate all 4 of the compounds. But based on the results, you might say, hey, instead of 25 to 1 ethanol, maybe we should try, I don't know, 15 to 10 ethyl acetate and ethanol, because 2 of the compounds didn't separate, or whatever the case may be. At the end of the day, our goal is hopefully to be able to separate all these compounds from one another such that they all have different RF values. But realistically, it may not work, okay? But these 4 data points, or 4 eluting solvents, will give us some idea of where to go next. Maybe we need to add a little bit more glacial acetic acid to the ethyl acetate and ethanol. Maybe it's the opposite case. We need something even less polar. So instead of ethyl acetate and ethanol, we need to try maybe ethyl acetate and hexane, because for whatever reason, all the compounds are eluting all the way to the end of the TLC plate. I don't think that's going to happen, but it is possible. If all your compounds go all the way to the end of the TLC plate, it means that your mobile phase is too polar, because your molecules aren't having a good opportunity to stick to the stationary phase. So you need a less polar mobile phase. Or alternatively, you could add ethyl acetate and not a single compound could move. Okay, and if not a single compound moves at all, said another way, all their RFs are 0, or all the compounds are just in one spot at the bottom of the TLC plate, then you may need to use a more polar eluting phase, mobile phase. And maybe that would be ethanol. Maybe that'll work. So the idea here isn't to necessarily solve this problem of separating these 5 compounds. The idea here is more to use these 4 solvents to get a better understanding of what you might want to do next, or how one could, make a different mobile phase that has a chance of separating these compounds. So I know we were throwing you a little bit in the deep end with this experiment because there's a lot going on here, and we're giving you molecules where it's not obvious which is more and which is less polar. However, I hope the experimental evidence will give you a better understanding of what is going on and whether or not it's possible to separate these compounds. I do appreciate watching the video. I hope I was able to answer give you some information about the pre-lab, and specifically the introduction part. Would like to point out that in this case, it asks you to predict, okay, the relative RF values of the analytes for a solvent that will separate them. That's going to be fairly hard to do, given these particular molecules. Although I can say that when we look at something like diphenhydramine hydrochloride, because it's ionic, we could be fairly safe to say that this will have a relatively low RF because it's ionic, and the other ones are just polar. Amides tend to be relatively nonpolar. Amines tend to be a little bit more polar. So here we have an amide. Carboxylic acids are pretty polar. OHs are pretty polar. Carbon containing groups are pretty nonpolar. So give it your best guess as to what's going to happen and try to defend your argument. Okay, so for example, one could argue this molecule contains a carboxylic acid. This molecule contains an OH and an amide group. However, it contains less carbons. So I think that relatively speaking, the RF of this one will be lower than the RF of this one. Said another way, I think this one is less polar than this one. Are you going to be 100% sure that that's correct? No. With these molecules, it's impossible to be 100% sure about which one's going to have, more or less polarity in a particular system of silica gel and a mobile phase. However, if you give it an honest effort, okay, you could say this one has more non-polar hydrocarbon type groups, and it's a good guess. Okay, will it turn out to be 100% true? I don't know, but your experimental evidence will show you. In the conclusion, you should have a much better idea of the relative polarities of these molecules based on how they elute through the compounds with these four solvents. So I hope that you found this video helpful, and I hope it gets you started in the right direction on your TLC experiment.